I have a question. How was your statistics course?
Oh.
Do you remember something from it?
Yes.
I remember something alright.
This is something we cannot forget.
Good. So I'll put the one of the cases first, and we'll try to solve it. Just what I need. Okay.
You manage a chain of 100 fitness centers.
I imagine a chain of one. Does that count as a chain? Within certain definitions of a chain. By a couple of orders of magnitude.
I had a use case at the end, but we will start from the use case, and then we will finish with trickier use case. Подождите, а у вас статистика была в R?
No, we will appreciate it. This time it will be in R. In Python.
It will be in Python.
Yeah.
Well,
I kind of wish we could just.
Or Java or Julia maybe. No? No, Julia, no.
there is a new language, well, new, it's already 4 or 5 years old, which is called Julia. And they claim that this is one language for investigation and production. So it is as fast as C++, but as nice to write as R.
But it is the popularity is growing in USA of this language.
I wanted to start to code in Julia 4 years ago, but I didn't. It's still domain-specific language, and I'll tell everyone. It's connected to decision-making based on data. In my perspective, the biggest bottleneck in technologies are not a module that does computation. It's its implementation and kind of how you connect it to the whole system. And the biggest obstacle is not switch from R to Julia. The biggest obstacle is to learn that engineering to make it right. In my experience, we used containerized code in R, which worked with a Spark server with those 8 billion profiles, and it was fine. It was not, well, it didn't work with 8 billion profiles. We checked all the profiles which changed, then sent it to a few containers with code in R, did our data preprocessing, partially in Spark, partially in R, then applied the model which was in R, and sent back the results. Which is exactly fine. So technologies are very rarely the bottleneck. The biggest bottleneck is humans who support technologies and how your technological solution implements in the whole business. If you will write a code that will work 10 times faster, unless you are working in the company which the core business is to work on data, okay, core business is IT, then it's critical. But if it's 500,000 rows of financial data, 10 times more, 10 times less means exactly nothing. If you are a search provider and you are Google, then it does, because that means that your budget on data center is 10 times more and 10 times less.
But with this article, the saving of 25 seconds to 3 seconds for this business doesn't really help.
No, for financial data, it doesn't matter at all. But if your business is processing data in enormous scales, then technologies matter. So, for example, Booking uses, well, it's tricky example. From one perspective, do you recall something from your course on databases? It's part of the course. So there is SQL and NoSQL databases. Most SQL databases, let's say, there is solid asset principles, like it's an acronym. So basically it's atomicity, etc. So anyway, NoSQL, SQL databases store data more consistently. It's difficult to explain in English.
Difficult to put in and easy to put out.
No, not in this dimension. Basically, they are very safe. Each transaction is atomic. You do not lose data. You do not lose transactions on the way. All the clients see the change at the same time. You're blocking the database or a part of it if transaction is in process. So it is fine for financial data. But it creates overheads in processing. NoSQL database, most of them do not have this technologies inside. So theoretically, it's cheaper to maintain. You need less server capacity, you can process more data. But, for example, Booking uses MySQL from Oracle. They use for analytical purposes, I think, Hive and Spark, but just for analytical purposes. Their production is in old, known MySQL. And they are saying that there is no point of moving the infrastructure to something fancy because everything will fail with this scale of data, and they have enough specialists, very good specialists, to work with the technology that they have. There is no point of moving it to another one which will fail as well. But they do not have human capacity to deal with the issue. So same here. Okay. So we finished that. I've named the task to build a cohort analysis. I'll write it down. Probably I'll write it down on Monday. You'll get the written form of the task after the course, but you'll get it, and you'll have decent amount of weeks to finish it. There will be no deadline in the next few days. There will be a few weeks to play.
But no decision here. We just built code in Python.
Yeah, here no decision. Well, here we talked about it. Yeah, so let's. So here, what I wanted to talk. Usually, this is a normal chain of SOCs for most people. Facts, conclusions, and testing, which is practice. In reality, when we're discussing facts, there is a lot of effort spent on validating the facts, if they are okay, etc. In reality, a lot of conclusions based on the right facts are wrong, and a lot of conclusions based on valid facts. There is no connection. There is less direct connection between facts and conclusions, especially in business. There is a statistical logic behind this. There is confounding variables. Нужно объяснить, что такое? I'll explain it in Russian. So, confounding variables — это переменные, которые мы не учитываем в исследовании. На самом деле они очень влияют на результат. So there are a lot of confounding variables in most of the trials, and when we create a conclusion, usually we miss something. So the only valid conclusion is that we've tested our solution and it works. So there is not much space for theory, especially in business. I mean, we still need to do right things to test better solutions, but without the testing phase, most things do not have sense. And we need to test thoroughly, mostly because human brain is not wired to assess probability at all. This is a list of top four biases from way bigger list of biases of human perception of probability. This is just probability. So basically, any average human is overly optimistic about desired outcomes, and so when you're building your solution or you're hoping that your hypothesis will work out, you're already overestimating chances of this to work out. When there is uncertainty situations, people also tend to judge probability poorly. But this is not a lecture on behavioral psychology. Let's look into the numbers of one counterintuitive thing. You have a particular business process. You start to improve it. You build first solution, second solution, third solution, etc. Each solution, and solution in this case, I mean a model. For example, you have a classification model. When you train your classification model, which metrics you would use after the machine learning course, basically? Which metrics you will use when you're training classification?
Basic confusion metrics.
And the metrics that you can optimize, because confusion metrics is 4 metrics. So you can get confusion metrics. And what you optimize actually, if it is one value?
Accuracy, for example.
Accuracy on balanced data set then? If it's balanced data set.
Precision. One of these indicators.
Have you talked on the machine learning classes about the metrics like log loss, for example?
Yeah.
So basically, it's the metric that penalizes all kinds of mistakes. So you have two class classifications, 0 to 1.
Yeah.
Confusion metrics, etc. It's you're either 0 or 1. Log loss penalizes the actual score if you have 0, 1, or if you have 0, 9. It will penalize both and will help model to converge better. So let's imagine the business process, and this is this graph from the paper which Booking published a year ago. Probably a year ago. It is a very interesting paper that I would recommend you to read. What it says that this graph shows a difference in business metric versus relative performance of the model. But it's not the first model, so we have nothing, then we have first solution, then we have second solution, and then after X iterations, we can improve things. When we take the same task here, for example, it was classification, and we have metric of the model metric, and we have business metric. So you put the data scientist into the task, he still improves the model. The model starts to classify better. But in reality, there is no statistically significant improvement in business metric. So basically, returns of any long-going data science process without restating the business process around it, you get a lot of improvement, then less improvement, then less improvement, and there is no improvement. but your metric of the model still can grow. That's the point. So if you do not evaluate your business improvement, your metric of the model also first grows rapidly, etc. And then it says, no, things might get better. But business doesn't notice the change. So basically the blue dots, so there are two scales. First is relative difference in conversion rate. They optimize the conversion, and then there is relative difference in performance. So in these two quadrants, we can see models that are behaving fine. So better performance, better conversion rate, worse performance, smaller conversion rate. But what about this and this? These are counterintuitive. We have, at least Booking has gotten better performance, but conversion rate dropped. Or worse performance, but conversion rate increased.
Yeah, this is like a pretty well-known like business phenomenon. This of chasing the wrong metric, you know, like.
It's a right metric at the beginning. Then it stopped. So at the beginning it was fine. And then after a few steps of optimization, this one metric is getting better and another one doesn't. So they lose connection at the later stage. So it's not from the zero model to first one, not from the first to the second, but from n model to n plus one. A further improvement of the metric as a data scientist doesn't improve business process at all. So they checked Pearson correlation and Spearman correlation. Pearson correlation is, do you know what is Pearson correlation and Spearman correlation? What is the difference between them?
I don't recall the difference.
Yeah,
I don't remember the difference between them.
So the difference is very simple. Both are correlations. Pearson correlation is a check of linearity. If this grows by x, this one grows by that. So basically, they're checking if it's linear. So this would have high correlation, this would have low correlation. Second correlation, Spearman correlation, checks correlation of ranked items, so it's test for monotonicity. It doesn't care how much better. Here the change in one metric, theoretically with 100% correlation, gives constant improvement on another metric. In Spearman correlation, it's monotonicity. It means that if this metric goes up, for example, with positive correlation, of course, then the next point has to be, it can be a bit higher or much higher. It doesn't matter. So you can have 100% correlation with something like this. It's not linear, but every next point is higher than the previous one. And in opposite correlation, you just draw the mirrored one. So the first one is about linearity, the second one about monotonicity. You do not care about the size of the effect, but you care about the direction of the effect. So there is no influence on the direction, and there is no influence on the strength of the effect. Here direction and strength, and here just direction. So there is no correlation, at least statistically significant one. Booking stresses that this is not between online and offline performance of the model. If your model improves offline, it is probably improves online if your setting is right. It's the connection between performance of the model and performance of the business. And this is a result, I think, of 150 successful models in Booking. that there is a particular limit. To overcome the limit, we have to restate a general problem or to change the business process where another kind of the model or another setting with different data points, etc. would kick in. Otherwise, we would stay here. In reality, probably none of the Ukrainian businesses are on this stage. You have to be extremely data-driven.
So is this something that's different than just like the law of diminishing returns that happens with like every effort?
It's same stuff.
Same
but
stuff. Okay.
but returns are diminishing, but they are diminishing with a different rate and different metrics. The one that you get it from the model, it still says your effort was good,
Yeah.
and the business already lost the difference.
Yeah. So the model is just not able to understand the idea of diminishing returns.
It understands it later than the business.
Yeah. So that would be all the real world confounding factors that aren't in the model. They put the limits on and the model doesn't.
Yeah, the model still says that it is improved, but it is not. So we are very far from this point, technically. Some companies in the world are there, but there is a very valuable lesson for the business. First, that first few trials are the most important one, and then we can leave it.
Something else.
And the biggest returns would be if we would properly restate the problem. If we would change the business process around it, that would give the biggest resource. So, for example, if there is if we're talking about marketing, if there are particular communication strategies, if I'll improve clustering by whatever metric for clustering, for purity of the clusters, for example, our business metric, revenue or engagement or whatever, will grow only moderately. If I will change the way communication is happening, I'll get much higher increase. So yeah, in theory, we think that the fact is that the quality of the model improved. In reality, this fact gives nothing to the business outcome after a particular limit. So, use case. You manage a chain of 100 fitness centers. Let's assume they do not have receptionists that sell or upsell to the visitors. Propose an experiment design and explain how you would calculate ROI of the change. And change means adding receptionist to the staff and see if you gain or lose money with this business decision.
Sure.
Because receptionists cost money as well. So you lose money, but you hope to do more upsells. You can have probably 5 minutes, 10 minutes, 5 to 10. You can Google, do whatever you want, propose an experiment design and what you would do and how you would calculate that this adding receptionist has sales for your business. Go!
Yeah.
No receptionists.
But we call them administrators. That's why it is not applicable.
This is actually a real task, not for the fitness centers, for different business, but the core of the task is exactly the same.
But if I can give some just propose one idea, maybe I hope I will not spoil the people. Here maybe the good idea will be to perform some kind of A/B test. I would say delay contacted 100 people. We take another sample or a few samples, 100 samples. How much to receive normal distribution, and we compare.
So propose an experiment setting.
Okay. 100 fitness samples. Okay.
It's 150 samples. It's slightly trickier.
This is interesting because this is exactly what I'm thinking about now in my project. Excuse me.
2 weeks ago, I consulted a department which was doing this kind of research without proper planning. So this is an actual task. Not with the fitness centers, not with receptionists, but it doesn't change the task at all. А повторить задачу? Так как вы еще не забыли статистику, я решил начать с use case. Use case следующий. Вы управляете сетью из 100 фитнес-центров. Предположим, это фитнес-центры без администратора. Вам нужно решить, как проверить, что нужно сделать, чтобы понять, если мы поставим администратора, который умеет продавать, или обсайт. Как нам понять, мы заработаем денег или потеряем? Как сеть? Мы сейчас будем разбирать. Мы сейчас к этому придем. By the way, this is standard statistical task, asked in a business language.
Теорию надо, да, то есть, предложить теорию, да, то есть каким методом.
Да, что нужно сделать, чтобы понять, мы в результате будем в плюсе или в минусе. Деньги на попробовать есть. Это не обязательно бесплатно.
То есть это мы напробуем, снимаем данные, а потом должны сравнить.
А потом должны принять решение, выкатываем все, или отменяем, или охрана отмена.
Мы должны работать с тестом.
Да, это правильно. Вот. And by the way, what I just said that we have money for the tests, so it's not pure theoretical test. We can do particular actions, hire people, see how they perform, etc.
Yeah.
But at the end of the day, we have to understand if our business is getting better or not. here is a list of the types of experiment design.
That's exactly what I wrote down.
So this is just the types of how you can design an experiment.
Self-speaking.
Well, this is mostly from sociology. In actual finances and computer sciences, you have much less smaller variety of the forms of experiment, but still there are plenty.
Do you know all of them?
No, no. I've conducted few of them. I've read about 3 times more than I've conducted, and others are very specific to sociology, which I would probably never do. It's just the indication that propose an experiment design is not as straightforward as you might think of. Because there are at least 2 ways of doing valid experiment design, 2 different ways. So how much time do you need to finish?
Yes.
Okay. So, how?
So it depends on the number of customers. I will start from the number of customers, and then it's 1,000 per one center or something like this. More. So let's say 200,000 to 2,000 per business center. So we have 200,000 customers. So second, activity to understand the. Okay, let's imagine this is active customers isolated. So this is after that.
Actually, you should calculate number of fitness centers we would like to include into our pilot experiment or something like that. And also we then should compare upsells from other fitness centers that are not in pilot.
How do we calculate number of fitness centers we want to enroll? Гуглить можно, кстати. Гуглить можно.
How to calculate? Well,
Kind of, what would be a number of fitness centers enrolled in the study?
well, it depends on how much we would like to spend on our new receptionists. If we I think based on 100 fitness centers, I think maybe 5 till 10.
10. I would do it based on the number of secretaries or receptionists I could put in a room and train to the same service standard at once. So I mean 10.
But we should start from the error, standard error, because the conclusion we will receive, the data we will receive, we will compare with the standard error. So definitely we cannot take one fitness.
Usually, how is it made? We should have like pilot fitness centers and the similar one, but without any activity, and then we compare, and that's it.
Split into
2 or 3 groups,
and how do we assess similarity?
well, number of customers, closeness to the city center, or maybe like with pool or without pool.
Number of customers. Just as an example, with pool, without pool, the imaginary stuff are fine actually.
Yeah.
Pool and Distance to the center.
Whatever. Yeah.
City. Center. Something else?
I wouldn't bother doing this for only 100.
Huh?
I wouldn't bother doing it. I would pick randomly for only 100. I don't think it's worth it to.
Well, I'm writing down all the
I know.
all the things.
Yeah.
So split into pilot and similar, or third group. There was third group. Third group. Or split randomly. Okay.
What I would try to figure out what the metric was that we're going for. So I pick a metric to measure as improvement. So I would say 6 months retention customers that are still around after 6 months. Target that as the thing that you're looking for. So that means that you need to do this for long enough that that will show up.
But we speak about upsells.
Pardon?
We speak about upsells.
Because
Additional sales.
it's easy just to measure, number of customers that we sell, bang, 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 bang. But I don't necessarily just want customers that can be turned around. What my larger business is based on having these longer term good customers.
Yeah.
So I would want to make sure that I'm not pursuing what's easy to measure, I'm pursuing what's actually of value to my business, which is longer term customers.
Okay. So if you speak about new customers, I think it is more cross sales than upsells. Because upsell, for example, the guy goes to you for gym, but you sell massage to him.
Sure. Yeah.
Or revenue can be also metric, but I wrote it after yours.
Blah, blah, blah. Yeah.
Okay. What else do we need to do? So we have budget constraints or organizational constraints, which means about 10 receptionists. Or consultants, doesn't matter.
And then I would set things up so I could measure these. I would make sure that the receptionists were working on schedules if there were different. So days of the week stuff was factored out. They weren't always working the same days of the week. I would evaluate.
Wait. So you want to fix that they work at the same days of the week, or they work in different
days. So because I think that you want to evaluate. Because at the end, I would want to evaluate not just a center that has any receptionists versus ones that don't, but also a center with the new type of receptionist against itself in the past, and a center with a new receptionist against itself on days when the receptionist is not working.
Mm-hmm. Make receptionists work different schedules.
Yep.
To evaluate different
It's like just opportunities to sell. They're not all the same.
evaluate more evaluate more options, different kind of engagement, right?
Yep.
Can we have situation when one fitness center, the receptionist from one city center will take customers from another center?
They're physical.
So separate, and the database, customer database also separate. I mean, the list of customers he or she will call, so the list are separate.
Well, see, I think, so what do we mean by upsell? I think we're talking about different stuff.
Absolutely.
Yeah. Because you're talking about calling people. I'm talking about you're standing in the building, they walk in the door, and you want the
It's the person that is on the premise.
Yeah.
Upsell?
Because for me, like,
Receptionist.
Yeah, receptionist. That does upsell. What is upsell?
Her first task is to talk to existing clients or people who walk in through the door
To buy more.
to buy more,
To buy more
or to buy.
or to buy it all. Yeah.
Well, basically, most people who walk into the fitness center most of them are clients.
Yes.
So by definition, it is upsell.
So that is why
Because fitness centers do not have much street traffic.
this person will not attract new customers.
Why?
This person will sell more to customers.
Mostly, yeah.
Everybody.
If
But
someone
she
will come from the street, she will help. But
yeah, of course, yeah. Definitely. That is why she's receptionist.
But you're saying that they're calling out.
Calling out, but what I want to say that this, for me, this according to this word upsells, it means for me that the person contacts with the existing customers, maybe. Yeah. Not with all the people to invite new customers.
But actually, this is not bad idea. We can also, in the same experiment, we can separate a group of all fitness centers with existing clients, and we can not add additional receptionists, but try to sell by phone, just to call to them and to sell by phone. And to see what will happen, and what will be more.
Yeah, because I think you're right. 'Cause for me, like at the bottom of my thing, like I think it's like a kind of a trivial thing that to have somebody upsell versus not having somebody upsell is going to result in more thing. It's sort of a trivial experiment. It's the with the budget of 10 receptionists times 6 months, how are the different ways? So it's like, so simultaneously, you have to evaluate other ways of spending that same money. Just doing only, should I have receptionists or not? It's like, well, of course they're going to generate more money. It's like, if I have the budget for 10 receptionists, I would pick 10 facilities where I said to the manager, okay, you have this amount of money to improve revenue here, so do whatever you want. And then I would have to my marketing person, you have this amount of money to improve sales, do whatever you want. And I would compare those three things, not 10 receptions versus 0 receptions, because that's like, of course it's going to be better.
Okay, I wrote down.
So what you say, I understood that you say that if we hire the receptionist, for sure this person will produce some upsell.
Something, yeah.
Yeah, definitely. But the question is yes or no. The question is how much.
Maybe we should also check kind of motivation system for receptionists, just to be ensured that they do upsell.
But yeah, the purpose of ROI is to compare two options. This is only one option.
Yep.
So we'll get a number X. So who cares?
Yeah, but we should understand how many business centers should involve to make statistically significant to be able to make the conclusion from statistical point of view.
That's what you're saying.
How many receptionists should involve? If you have 200,000 customers, how much we should control? And here I remember our example on Romankov's class. We had an example of USA elections. USA elections, president elections, and there was a situation when the guys called to 1,000 people, and the confidential interval was like this. They decided that this is good enough. So they came from the number of the contacts to the standard error to understand the confidential interval. So if you want to finally to come to the conclusion with the confidential interval of 95% or 90%, so then we should find that figure also. In president election example, it was 1,000. In our case, it should be how much? 10, 200,000, how much? One fitness and maybe also okay. So I think in formula how we will calculate the final statistics.
Final statistics?
Yeah, I mean ANOVA, or it will be. We will compare average with average. We will compare.
Yes. I think here the main task here to check whether it's statistically significant difference or not.
Yeah.
Yeah.
So for this there is specific set of requirements. Yeah, how many samples shall be done?
To be in this normal distribution.
Yes.
So, how many samples should we take?
Magic number is 20. 20, or 18. I forgot.
I'm writing all the assumptions here. Because we came to a trickier way than group by tables and count and some money. But actually the essence of data-driven decision making is here, is when we're approaching right now. Because same principles would work independently if you have a receptionist or if you have a machine learning model or other things. So number of centers enrolled. Let's say 20. 20 means in each group or in separate groups. Kind of 20 divided by 2, 20 divided by 3, or 20 plus 20.
In each group, you say?
Yeah, I'm asking what means 20, magic number 20. It's 20 divided by the number of groups, or 20 multiplied by the number of groups.
Number of samples.
Yeah, kind of what is the number of samples, what is the number of people in group? For this number 20.
I don't understand the question.
I didn't get it.
Yeah, so I've heard the following, that to calculate if it is statistically significant, we have to understand how much fitness center we have to enroll in the study. Then I've heard that there is a magic number which is 18 or 20.
Mm-hmm.
So 18 or 20 is two groups, one group, kind of. I'm trying to dig deeper into what we can apply this magic number.
More precise to make this stratification. Yeah. So when we divide it on different classes, yeah, because it could be elite class, yeah, it could be school, whatever, yeah. So it's more precise, yeah. If you have stratas, yeah. So for this, but maybe for the first it would be enough just.
I think I wouldn't bother segmenting at the beginning.
Yeah.
At the very beginning of the thing, I would just say like 20 in total.
20, yeah. Total.
Yes, if you will have 20 samples, then we can easily calculate the normal distribution for the mean.
Actually, why to calculate this normal distribution and so on and whatever? Just I think for what? I think
it's
the task is quite simple. Just you have like a normal rate of revenue, then you add something else, and you see like high revenue, or you see nothing. And
But it's proving it's not chance.
Yeah, but
it's
maybe
not
it's
highly
just-
variable. It's not the weather. It's not.
maybe it's not statistically significant, yeah, just within this distribution, yeah. Just
like actually in business, if you don't see like extra level of revenue, you don't calculate any statistical significance. You just stop the experiment and what to calculate so complicated things.
because maybe you have this growth, yeah, but in fact, yeah, using houses for 100 of gyms, yeah, and you will get actually lost, yeah, because you will spend more actually than you get, because your previous profit was just random, yeah, so it's not.
No.
By the way, what is the target value, target metrics?
Well, that's what I said. That's what I was saying.
6 month retention?
Yeah.
Stop. Wait. Can we go step back? Stop experiment if there is no revenue growth. What is no revenue growth? Like zero? There is no changes.
like no changes, or we don't like see any significant added value from this experiment. I don't know. Maybe we should accept kind of a tolerance in revenue growth, or maybe revenue downturn. In this case, just before we start experiment.
Okay, so but this is basically there is a particular rules in addition, which we can do early stopping of the experiment when it is clear that it doesn't work out. Okay, and then there was so I wrote it down. And then you were on discussion that what is our metric?
Yes, because it's very important. Again, if you speak about new customers, then 6 months retention is okay, good metrics. If you speak about existing customers, so then we should focus on revenues or wooden upsells, just upsells, number of upsells, without revenue. So another metric.
I write it down.
Depends on that. In fact, it will not change our experiment. But
You could look at multiple metrics.
but for 6 months you will need 6 months.
Yeah, and the reason I'm saying that is because it is possible to oversell to your members and to turn them off and have them to leave because they actually get tired of the upsell. So it's like there's a core metric which reflects the center of your business, and you don't want to create a thing that says, "Oh look, we've sold all this, and look how many people we bothered on the telephone," and you lose the actual core metric of the business that is the one that drives 80% of your revenue.
Or not on telephone, but it's scary to enter the fitness center because you are bothered at the entrance all the time.
Yeah. So you need to pick. In my mind, you're picking something that's far enough away from the immediate effects of what you're doing that it's not poisoned by the very fact of the experiment. It's like deeper in the business that you're seeing the slow moving of the boat and not just the shaking around of the...
I agree, but better not to start an experiment if there is significant risk that we will lose those customers. How we will be sure that we will not lose, that metric Igor proposed, this metric that we should stop the experiment if the revenue goes down. Some of the, also we should stop the revenues. We should stop the experiment if we see that something wrong with another metrics.
Unless the profitability increases.
It's again, this drop shall be statistically significant, yeah, so you shall check if it's...
You should check, but very quickly.
Guys,
You are overcomplicated, you know?
You lost first part of this day. You did not know what metrics you
why I did so, because I'm solve it simpler, you know? I don't want to be as clever as you know?
Okay, so did your list of hypotheses exhausted?
Oh,
Or you still have more?
For me, the biggest thing is to make sure that actually you are evaluating enough other things against this at the same time.
I wrote it here. Evaluate other options to spend, and my perception is to work different schedules, evaluate more options, kinds of engagements.
Yeah, and I think it's possible to run those all at the same time.
We'll see.
You mean in all the 50%?
No. You can have them simultaneously. You can say you 10 people do this, you 10 fitness centers do this, you 10 people do this.
Again, this is for beginning.
Okay, this is the beginning.
Not everything is
it's also standard technique A/B testing, yeah, so
Kind of testing.
B. And C is do nothing.
Well, okay. So, what would be amount of business centers we are enrolling in the test? Let's write the final segments. What do we test?
Up to you to decide.
Huh?
Up to you to decide.
Oh, the easiest way is to split them half, like 50 to 50. But actually, I'm thinking that it will be too expensive just to extra stuff.
Okay. So how do you split them? How much fitness centers do recruit? We had the idea that 10 receptionists. I've heard magic number of 20, but I do not know it's 10 is a half of 20 or 20 plus 20.
Oh, in statistics there is number, yeah, when...
Just say number. Please.
Ты имеешь в виду Парето руль?
Не. Там вот есть именно конкретно, что если меньше этих центов,
Yeah.
да, тогда мы по...
But I don't think it's as high as 20 though.
I think it's...
Otherwise, think about polling of countries.
I propose two samples.
You don't need to poll 20% of the country.
No, let's do.
If you
And
were,
this is
if
the
you,
good
if you
idea.
were, if you had a production line, you would need to test 20% of the production. 20 seems like a very high number.
No, it's not really about the percentage, so it's in principle you should have some kind of minimum number of samples. Yeah, so
That's cool. You're right. And say number.
let me Google it.
The thing is, you can get lots of data through like numbers of centers, but also through over periods of time.
Okay, we will take...
Let's make 20 pilot fitness centers.
We will take 10 receptionists and 10 fitness centers who will encourage upsells, and 10 which will discourage upsells.
And another 10 will close down.
In principle, you can make one fitness center 1 month with administrator, second month without, then again with administrator without, yes or
Well, this is why I was saying with different days. I think you could compare one center against itself on different days, right?
No, I don't agree actually with one fitness center. I think if we have larger amount, we can try with.
No. I think I would do like 10 receptionists, and I would get the more information by like taking more out of those 10.
It may happen that it takes time for people to make decisions.
Yeah.
So she made
One
an
month
effort,
is not-
it worked, but then if you say okay on Monday
Let's
you
let's
add
make
on Tuesday for example, on Tuesday she might
I like
This way,
find my book.
I don't know why, but I
put
like
them a card with a
Let's boil down to the final setting. Because it looks like we exhausted all the hypotheses. Let's boil down to acceptable final settings.
Yeah.
Not the full list. I'll leave the full list on board. We will go through the course and we will see what goes where. But just for some calculations, I would like to fix the final one, even if they're not perfect.
Okay, let's take 10.
You are board of directors. You have to find an agreement.
Oh, I'm CFO, no money, no experiment.
I say 10. 10 allows you to actually
Yeah, 10.
train 10 people.
I like 10.
10 in treatment.
There are 10 locations with 10 receptions.
10 in treatment and 10 is, how do we control over what we control? 10 in treatment with, how do we compare the result with what we compare result? 10 with all the network, 10 with,
We can
10 with similar ones, 10
I
randomly.
picked 10 random.
10 random, and we should then compare to another like similar 10s, and also we should compare 10s before experiment and during experiment. So we should compare like how to say in time and also
Too much.
You want more than 10? You want more?
I think it depends. Yeah. So first of all, which confidence interval, yeah, we want to have, yeah, depending.
Which confidence interval do you want?
Depending on
95%.
this, because the more accurate we want, yeah, the more samples we need, yeah. So it's
Yeah, well, it is slightly trickier than that, but I would like to write in assumptions.
10 treatment.
It's not very tricky. You'll see. So anyway, 10 random for treatment. How we
wait, yeah.
so 10 competing with 10.
yeah.
Oh, no, I'm just
But-
repeating the manual.
Why we cannot calculate upsells metric, and then we will compare this the increase, the change of upsells network, the upsells for the all network except this 10, and upsells metrics for this 10.
Yeah, so
This
it's
is
90 and 10. So basically 10 versus 90 or 10 versus 10. So we also have two choices. Similar ones, independent choice. Similar or random. If we select 10 versus 10. Okay? Good. What else? How do we understand that? Metric.
The metric.
The main metric is as far as I understand, everyone agrees that the most important one is the one that is far one, like 6 months retention.
This is only what I say. Others may disagree.
Do we have some metrics that we can analyze faster?
Revenue, the number of upsells.
Revenue and upsells. This is fast.
Number of. Okay.
If we know what kind of product they do upsell and we know the cost of the product, we can even calculate or just assess kind of profit.
I wrote 6 months noted. I wrote 6 months retention as a long metric because some experiments are worth keeping for a year, some are not. Anyway, so we have to have fast metrics as well. Good.
And are we going to evaluate other options at the same time or no?
Yeah, good question. Are you going to evaluate other options at the same time?
Yes.
We're evaluating one other option anyway, which is to do nothing. So we should have a second option of a similar cost.
Actually, I would like to try kind of telesales just for
What's right?
upsell by phone. Just
There you go, sure. Pick telesales.
I'm writing +1 experiment. Phone sales. Okay.
And if this really was my business, I would pick my 10 best managers and I would give them the budget and I would say, figure it out.
Or
Yeah,
an alternative.
yourselves, yeah.
Alternative.
The next general manager is whoever does the best in this competition.
10 best managers plus budget. Good. What else? I think it boils down to something. Okay? So let's carry on.
And now we will hire data scientist.
no, never.
Yeah, okay. We will come back here later. So, that's what we might have with continuous values. You can have a control group, treatment group, or other way around. They can have large variance, so basically they're whatever target metrics we are choosing or we are monitoring all three. For the first one we do fast decisions, but we are getting entirely sure of experiments on the most important one. For example, if your main metric or whatever metric we're analyzing is has large variance. With large variance, we can actually notice only big changes. If our metric has smaller variance, we can notice smaller changes because of the big part of the distribution is shifting. And basically, there is a metric which calls statistical power, which means the following: a probability of alternative hypothesis being true when it is actually being true. So when we're doing A/B test, standard statistical power is 90%. which means that if we will put in 10 tests 10 positive hypotheses, we will confirm that they are positive only in 9 cases out of 10. This is industry standard. I'll explain why. Soon we'll understand why it is 90%, not 95 or 99. Actually, because your length of experiment and amount of traffic or time you have to spend on experiment will grow exponentially. So 90 isn't bad, but 90 isn't good either. But basically, you will lose one good idea. And again, in industry, especially in online trials, not in offline trials, many companies fix 10% error rate for false positive ones. False positive. Right. It means that in 10% of the tests, we will think that it works, it earns more money, but in fact it doesn't. Most statisticians like not 10% but 5%. But again, randomized online trials usually have 10 and 90.
What is the exactly confidence level?
It is kind of confidence, but for hypothesis testing, because confidence is for one value. Kind of basically, here the
confidence
confidence is p-value.
Probability. This is proportion.
P?
No, it's
P-value, this is proportion.
alpha. This is alpha.
It's not that.
This is alpha.
Yes.
This is confidential
Level. Yes. There is confidential interval, there is confidential level. This is confidential level. Alpha.
Интервал не смотрим интервалы. So basically, our hypothesis testing has to accept or reject a particular hypothesis, which is the business one. So let's see. Wait. I will go through experimental design first, at least the theory of it. So there are many kinds of experimental design strategies. And one saying is that the hypothesis has to be stated in writing in almost all cases. That's why I pushed
I forgot
you.
to say, it goes up by 10% sales.
Increase whatever metrics we're
Increased by more than the cost. Plus 10%.
increase by 10%. Okay, good. So first we have to fix the experiment and experiment setting. It actually sounds redundant until you start analyzing someone else's results. When you start analyzing someone else's results, you see a lot of this. It's another bias that was not on the list of bias. In Russian, it would be «я так и знала». Это же было раньше понятно. In statistics, it's called hypothesizing after the results are known. And it's actually, there is a series of behavioral psychology papers on cost of hacking in applied science, not in applied science. Some people say it might have positive effect as well, but it actually happens.
Do you know that hark means to look back in your memory? That's what the word in English is, hark. To look back in your memory.
Interesting, because this is exactly about that. And this is one of the research papers about hypothesizing after the results are known. And this is an actual slang in the cultures which do a lot of testing. So these are not all types of allocating participants in groups, but we mentioned something which is similar to, well, which is actually random, and randomized block design. Randomized block design is basically, in sociology, it's the simplest one. For example, you balance group 50%, two random groups, but you balance them to have 50% of males, 50% of females. And then you fix the big cohorts and then enroll them in a study. Some of them, let me check. This is all other types of experiments. We have by similarity. Let it work special, util.
Right.
Yeah, it's not right. It's since we are looking for similar stores, it's a particular kind of experiment which I cannot really. It has to be here, but the list is long. Anyway, this is possible, but we have to eliminate or minimize the influence of confounding variables. It's the variables that we do not take into account in our experiment, and they can influence our target variable. And this is the way to bring a lot of confounding variables into the experiment when we look for similar stores. I've seen it with my own eyes, how analyst looks for similar stores, well, not shopping, not sports centers, but similar stores, and then we start to look why the results are weird, and then we find out that the control group was checked as the best stores in the chain. They were enrolled in the experiment. Then we started to look there similar stores. We have found some, but the results are totally different. Our statistical our hypothesis check if they're actually correct were totally broken. So we couldn't build an analytical case out of it. But this is possible, except if we assess similarity, the list of criteria has to be super long. Otherwise, we bring a lot of uncertainty in the test. Then, if it's possible, we have to reduce variability. And very often it is impossible, especially if it's random groups. In statistical testing, there is a method which helps to decrease variability through statistical measurements before enrolling into the test and then during the test. But maybe we'll discuss it later, maybe not. I'm not sure, but in any case, I'll send you the blog post from Booking and the paper from Netflix. I think it is in the reading list, which is already on the website. Or not, but anyway, if it is not, I'll add it to the reading list. So reducing variability is possible with mathematical methods, or we cannot really do much things if the general setting is right. And then we have to control sources of variation. And this is actually the problem here. Make receptionists work in different schedules. Yeah. I'm not sure that it fits. These are different directions. If different centers would start to work different methods, we will increase the variability.
No, I mean the same receptionist in one center works different times. Don't just hire somebody to work the same shift. So the same receptionist in the same center working not the same shift every week. Because this huge time of day effects
to meet different people.
To meet different people, yeah.
Yeah. So it has to be okay.
Yeah, no, it's not every center could have the exact same schedule, but the schedule should be designed to show this, to have receptionists exposed to different parts of the business.
But then but it has to be similar in all treatment.
Yeah.
Because if it is different in all treatments, then we are improving variation. So then our statistical tests become more difficult.
I'll tell you my thought process. We have 10 receptionists. A receptionist works for 40 hours a week. A business is open for triple that. And so you want to have, and when you scale up, you're eventually going to have receptionists working all the hours that you're open. So you have a receptionist working different shifts to see because if you, let's say you have receptionists working 9 to 5, and you go, oh look, it makes a big difference. And then you scale up, and now receptionists are working 6 a.m. to 11 p.m. Perhaps the effect of a receptionist from 6 p.m. to 11 p.m. is null or negative.
Yeah.
And so you've only evaluated a small segment of your business. So the idea is that the receptionists would work different parts of the business.
Right, but it has to be consistent. It
Right.
has to be same through all the experiment. If we want to assess more, we have to repeat the experiment. For example, a receptionist who works first part of the day versus nothing versus receptionist who works second part of the day.
Again, in I was doing those at once. 1 week morning, 1 week afternoon, 1 week thing.
And this increases the variation. So why? Theoretically, if you have huge effect for a lot of fitness centers and trials, it will be fine. It would be a multivariate testing, different groups, etc. But in reality, when we'll start to calculate the numbers, we'll see that we're barely enough into traffic, human traffic and number of centers to be statistically significant even with one kind of experiment.
I take the criticism, thank you.
So, how can we be sure that our random choice is actually random?
Google random number.
With the stores, it's relatively simple. We take the random number generator, assign it, filter top 20, etc. But if it's not actually random, for example, in online tests, we can recruit users, except when the page is rendered longer, a particular type of users can be discarded from the test. So it's same abstraction leakage. Our recruitment process, especially if it is automated, in online tests can introduce bias in the recruitment process. And we can only understand it if we dig deep into how it is built inside. For example, in Google Optimize, as far as I've heard, there is a threshold. It's an engine to conduct online A/B tests for free. But as far as I recall, there is a threshold on time of the rendering of the page. If you force them to render a page faster, sometimes it says, I'm not entirely sure if the page was rendered properly, so I'm discarding this user from the enrollment in A/B test. And this can be dependent on computer on which user is using, internet provider on which user is using. And without understanding what is underneath, our automated selection process, especially if it is high-tech, can be biased. And this has actually happened not this, but very similar situation actually happened in Booking and all the big companies who do automated tests. And one of the things which actually happened as well, that, for example, photos online are loaded asynchronously. So you do not load first, second, third, fourth. You load it in with parallel channels. When one is waiting, another is loading, etc. So they appear in random or not controllable sequence. And when we are building a recommendation engine on which photos we have to show first, and they're loaded in weird sequences. Our implementation of the loading of the photos corrupts the sense of our A/B test, and it actually happens. On the business scale, when we just selected 10 out of 100 in Excel, it doesn't, it is fine. But when there is high-tech component, we have to dig deeper or hope that everything is fine. The trickier it is, the more problems can be there. Then we will come back to, yeah, let's go directly to the Power Calculator. You can check you can Google Booking, Power Calculator. I'm jumping through the slides because I am accustoming the program now.
So if
To another.
you make movies for Netflix, you should make sure to have fast loading graphics when you submit it to Netflix.
Yeah, it actually depends on the delays, on the way the technical implementation is actually done. Because sometimes we have very weird effects. Or for example, depending on the response time, you can have different bounce rates, and that depends on the response time in some technologies. So if you add delay, you recruit more people or add a fraction of people into your survey. But this is very specific to particular technologies. With the stores, everything is very clear. So this is a power calculator. This is basically, they are similar. This is a project of Skyscanner, this is a project of Booking. Except the project of Skyscanner is, they have not so beautiful statistics tools, but they have more tools that would force you to frame your hypothesis. Because you have to write on what grounds you fix it, etc. Let's see. Let's assume we actually made a random treatment here, 10 random centers. And our metrics is revenue, the faster one. Wait, what do we have about the revenue? Bad luck. Yeah, so our test would look like following. Need more. Our test theoretically would be like this. Our centers without a treatment have a particular distribution of the incomes in between centers, and it is supposed to be normal. Our new centers, or centers with receptionists, might perform different way. They might be on the same place, they might go down, or they might go up. And we expect that the shift would be roughly 10%. Well, it's not in percent, but anyway, let's say 10%. Good. So here we are. But if we're talking about 10 centers, we have 10 centers here. 10 centers versus 10. And now we have a slide with normality test guidelines from Environmental Protection Agency. They have two neat books. One is Data Quality Assessment Statistical Methods for Practitioners, and another one for reviewers. It's, I think, 200,000 page manual statistics, on applied statistics. which is very easy to use. They do not have all the tricky math. They just say what to multiply and what. Just follow the procedure. And the best part that it has statistical recommendations of what it has to be used. We have a sample size of 10. Which methods to test normality works with a sample size of 10? Either this one,
Student.
this one.
We know student.
Hmm?
We studied student in statistics classes.
This one?
Yes. Student
T-test,
range test.
actually.
Yeah, so the entire range test. Okay.
And skew is it's of course, but
No. So it's greater than 50.
it doesn't feel yes. So no kids.
There is another way. This is not the whole list of tests. There are visual tests for normality as well, which can be frequency histogram, probability plot, mentality plot. We will plot this. We will plot this in practice. But anyway, we have to assess probability distribution.
If I make one question about this distribution, in worst case, the shape would be absolutely different.
Yes, and
It would be
then
flat instead of
like this.
Yeah, one could be like this, and another could be like this.
Yeah.
In the worst case.
Right, it is possible. The trick then ANOVA and other statistical hypotheses will not work out because they assume that
Normal distribution.
they assume not only normal distribution, they assume same shades. Yeah. So that's a problem. Here is we will go through. Wait. Yeah, so it's two sampled t-test design. And this is an assumptions for calculating the sample size. So data originates from normal populations. Normal population means normally distributed. Population with normally distributed feature that we are studying. So we hope that they both normally distributed. Well, a sample of 10 stores is very minimal. We are getting into trickiness of the small sample sizes, which is advanced statistics actually. That's why there is a magic number of 20, which probably not magic number of 20 because I've never seen it in the books I've read, but I would prefer much more to work with 20 stores and distribution than with 10. Because when I see all the statistical guidelines, when you have small samples, everything starts to be very weird. But hopefully we trust our general population, so hopefully they are normally distributed. The variance of each sample are equal. So we have to check if the variance of this and this is more or less the same. Otherwise, if we will compare this kind of test with this kind of test, our statistical tools would probably not work well. Any statistical tools will not work well. It means that something is wrong with an experiment design. Because how come when you are selling when something is wrong? Then, variance estimate is reasonable and representative of the populations being sampled. It means that other stores have to have similar normally distributed and to have more or less the same variance. Population values have not to be correlated. In this case, it's not a problem, and it is random sample. But this we are controlling on the experiment design stage, and everything else we have to check during the data collection stage. And some of the things can be estimated visually. You do not need to put everything in formulas. We'll go through the practice. We'll practice both formulas and visual things. When you are working on the manager's level, you can decrease the risk just by plotting data and just looking at the graph. If we want to make it more clear, then we have to use some tests for normality, and only after that we can enroll our data into the statistic tests. Wait, I'll share the screen. Every time I'm running full screen mode in presentation, it switches. So this assumes our continuous metric. Let's try to see it in the visitors.
This was one of the links?
Yeah, this is one of the links. Booking power calculator. This is a calculator for online randomized trials. Let's say total traffic, so continuous metrics. How to use. Yeah, so look, we have to understand what was our value and where it grows. Well, in this case, it's for online tests, so it doesn't fit well to what we do. I'll set the power of 80, statistical power. Yeah, let's just estimate the sizes. Okay, let's take the simpler case.
What actually we are doing? So what actually we are doing here?
Yeah, I'll show you the simpler way. Let's take the binomial metric, which is simpler to play with without a distribution. For example, you have I don't know, a store which has a conversion rate of 3%. This is base rate, and this is binomial. We'll switch to continuous metric later. It's just it's simpler to start with binomial. We have 3% base rate. We think that it has to grow to 3.3% by 10%. So I'll zoom our calculator. Yeah. So our base conversion rate is 3%. We assume that it will grow by 0.3%. It means by 10%, right? We need 116,000 visitors per sample to get 10% false positive rate and 90% power.
90%.
I put them here. It was 80, now it's 90 and 10%. So when we have binomial, for example, conversion rate, he clicked or not clicked, he bought or not bought. And we expect the growth by 10%, from 3% to 3.3%. Either way, because this is a two-sided test, so we are looking for statistically significant changes either to 2.7 or to 3.3. We need to enroll in the test 110,000 participants in each group. So when it's just for you to feel amount of people required for the test. Then there is another trick. If your conversion is 50%, it makes situation completely different. It's enough to enroll 3,400 people in the trials. And if you expect your absolute growth being even bigger, for example, you have 50% and now you're expecting 70%, it's enough to have 200 people. So the smaller is the base rate and the smaller is the effect, the bigger sample size you have to find. In the cases of the stores, With continuous metric, it's the same, actually. But it really depends on the standard deviation. The smaller standard deviation is, the smaller sample size is good for us. So, for example, this is again for A/B testing. Let's say, let's even a bit rephrase the use case. Otherwise, we will stuck in the math right now. We would measure not the revenue, but number of upsells or conversions. For example, or probability of kind of conversion to buy membership for the next month. Conversion to buy next month. And that's totally different situation. So you take your store. What is the conversion in general for the people to buy subscription for the next month? 50, 60, 70%?
Lower than that. To buy the next month, it's not, that's,
If it is monthly.
that's a continuing thing, so it's not really an upselling.
Well, yeah,
Yeah,
if
so-
it's subscription based, if it's not subscription based.
Yeah, so that, wouldn't know that.
Whatever, let
Yeah,
it be 50%.
Sure.
We are accepting it to grow from 50 on relative 10%. So it grows either, it falls out to 45 or to 55. And then what base standard deviation do we have? If it's very steep curve, all stores have the same base conversion. Then we just need 2 people to buy. But the conversion base standard deviation of 1 in the stores are impossible. If your base standard deviation is 30, you already need 1,200 people in each group. Basically, it's 1,200 sales in each group. For example, we have 10 stores, 2,000 people per store. So basically, you recruited 20,000 people in treatment group, which is fine. Wait. Yeah, this way is better.
Let's say it daily and
What's the second one? Base versus all.
calculation of the impact, not sample.
Let's do the following, because I think you are slightly scared now of the mathematics.
Slightly, not slightly.
The new visitors, daily visitors, I guess it's a website.
Yeah, it's for the website, but the math is exactly the same.
So if you could, what is it outside of website? What does these mean? The total number of new visitors means sales.
People who came for the sales procedure.
Yes, but nothing to do with success or not.
Yeah, it's nothing. The base average is about success.
So 50 successes. Base average is successful sales.
Yeah.
The 1, 2, 3, 4 number is number of people you attempt to sell to. Right? Is that correct?
Let me rephrase for the binomial metric. I'll check the numbers because I do not like what it shows.
Should it not be base versus one variant in your experiment rather than all variants?
Base versus all. Well, they do not change. So in this case, it doesn't. Yeah. I would propose to calculate it in Excel actually after the break. Not in Excel, in Pandas. In Python.
Поэтому строить, но смотря, если строить по версии,
Ну, а откуда ты узнали?
когда версия Linux,
A couple of years. So it's, since I started taking this course, I know.
может быть там что-то на максимум какая-то не выжившего дата-сайентиста.
Свистнули это в Канаде, да, наверное?
Like the United States map, like that's
Правда? Ну, так тут
I always been the most
So let's finish with rough power calculation, then we will dig deeper. Then I'll especially calculate some few simulation for this use case over the evening, and tomorrow we will dig deeper in continuous variables, statistical tests for continuous variables. Because I feel that they will bring a lot of confusion. And we do not need to go through, I mean, we can go through a statistical kind of course, but this is not the point of what we're doing. So, let's go from another angle. This is similar statistical calculator, which is built by engineers from Skyscanner, which does same calculations but opposite. We just need a power analysis. So basically, in our 2,000 people per fitness center, let's say, for example, if we test an upsell procedure. By the way, it's upsell procedure. So we're considering that they are still buying. So if we're measuring an upsell procedure, the rates would be 1 to 2 to 3% probably. Because they are, for example, So let's simplify the setting for the sake of today's day. Same situation, we have 2,000 customers per fitness center, 10 fitness centers. 200 people per fitness center multiplied on 10. Each person comes, let's say, at least 4 times a month to the fitness center. So it is going to be 80,000 visits. Let's assume we take a very simple use case, pure upsell. So, for example, the visitor has to go to the massage or whatever, any additional procedure, and not in the case of contractual agreement, step into the next contractual agreement or whatever. So, there is a particular rate with which people are being sold massages in the fitness center. Usually, I would say fitness centers do not do 80,000 massages a month. They would probably do 800. 800 divided on 4, it is 200 massages a week.
I'd be pretty happy if I was doing that. If I think those numbers, I'd be pretty happy. Those are good numbers.
Да.
If it is 800?
Yeah.
Okay. So let's say there is a certain process, 400 people are buying.
Maybe it's at MMA gym that they have 80,000.
Then we put the staff to the upsells. This calculator shows an opposite, a minimal detectable effect. This is a slightly worse. Eventually, let's first calculate and then I will tell. So it's 80,000 visitors per month. So theoretically per day it's 80,000 divided on 30.
2666.
Good. 2666 visitors. But this is just a treatment group, so we have to multiply on 2 because in this calculator, the visits per day seeing the change, basically the sales is twice less, so we multiply it by a factor of 2. Basically, this.
563.
Yeah, 5333. So this is our amount of people which enrolled every day, which comes on the daily basis to 20 fitness centers. 10 of them are showing a modification, trying to upsell. Our base conversion rate, we decided that it is going to be 0.5%. So in 4 weeks, we will be able to see increase not smaller than 22%.
So, I mean, the statistically significant effect will be should be higher than this one.
Yes. So if there will be an effect of plus 15%, our test will say no, nothing happened. This is what we can do in a month. In 2 months, basically, we can detect an effect of increase of 15%. In 3 months,
6 months.
in 3 months, we can detect an increase of 12%.
So we're trying to measure 10%, so we need to go even higher.
Yeah. So we need to take
16.
Yeah, at least more.
20 weeks.
So in 20 weeks, we will be able to distinguish if effect is bigger than 10%. If the effect is smaller, our statistical test will say nothing actually happened.
Can it say it from the beginning, 6 months? Without
Yeah, but if the base conversion rate is 0.5%, if it is 5%, the things will change dramatically. We will see even the slightest improvement. If it's 10%, it would be even better.
What is the conversion rate in this case?
We simplified the case. The conversion rate in this case is number of massages. Fitness centers doing
Percentage of massage.
yeah from visits. So
10% of the people who walk through the door get a massage.
no, it's plus 10% conversion rate.
Yeah,
in this case it's 10% of it.
Yeah, there.
Or whatever kind of individual for example, we're selling individual trainings, not for the climbing. For example, 10% of people who are coming into the fitness center having so from 80,000 visits, 8,000 visits are individual trainings or group trainings, whatever we're upselling, and we have a capacity. So when we start from the higher base rate, our statistical tests gain power way faster. When we're trying to detect small change, it's tricky. With continuous, there is no decent calculator for numerical values, for continuous values. So I want to do at home a simulation for you how standard deviation influences the statistical power. So how statistical tests would be different between use case of this distribution of the income and this distribution of income. It's actually the same. When we have a steep peak, we can detect a small change. If we have a long peak, this kind of change would be not detectable. We have to detect bigger difference, or to have more data.
This example, this presentation, I think it is very good to explain the situation of
Sales funnel.
So retention, when you have new customer, so you have 100 new customers, but only 50% of these customers comes to you.
Well, it's usually not 50%. It's usually not 50%.
No, 50, but in 30% or something. I mean, in the retail business like this.
It totally depends on the industry.
It really depends on the industry, but statistics is more or less the same.
And here it's very convenient to see. And for example, if you put 50% conversion rate, it is enough to make this experiment during 1 week.
Exactly.
To see significant effect.
Yeah, if effects are big.
No.
But for example, if you have a super high conversion rate, somewhere 30%, and you do it for 1 week on such traffic, you can see only 5% improvement.
Yeah, but
5% improvement, in fact, it's a lot for the business. Because if it's the beginning of the sales funnel, you basically, with more or less the same costs, improve your revenue by 5%.
That's cool.
Yeah, that's cool.
So, but the trick is that we cannot see changes smaller than 5%. So if we have 2% improvement, we will not see. And there is another change. There is another trick. It's two-sided test. We will not see if conversion drops by 4%.
So this is comparing our 10 versus 10. So if we compare our 10 versus 90, so percent of visits that see the change is only 10%. How does that change?
Let's see. Let's do the following. We have 90. Let's do the calculation.
yeah, if you put 90%.
Yeah, we have 90 centers. We have 100 centers.
Yeah.
Every month, 2,000 people come into our centers.
Yeah.
And in general, they come 4 times a week, 4 times a month.
Yeah.
So we have this amount of monthly visitors, and now we're doing daily ones. And daily ones is 26,000 daily visitors.
Times 2. Or no, not
Yeah.
times 2.
And only 10% of people see in the test. And we have more or less the same stuff.
Yeah.
If we're aiming at conversions rate of 0.5%, we still need same 20 weeks to see the difference. Because our treatment group is the one that is the weakest. So if we're able, so in online A/B tests, there is often a desire to make it on a part of the traffic. And the only benefit is that you do it multi-day, so different people can come different days of the week, whatever. But you still have to find the same amount of people. And the other problem is that this test would not find a decrease in sales by 8% with the settings, because this is two-sided test. Unfortunately. So basically, to make a decent test, you need to have a good sample. Let's go back to statistical methods, and then I'll show the same troubles with continuous values, because they are exactly the same. So, regarding decision making based on data, scientists are doing it all the time. General science paper has all the tools to make statistically significant results based on the data. This is a random paper which I was reading. It's about influencing how exercise influences snoring. We need only methods, inclusion, intervention, randomization, and statistical analysis. Let's open the paper and see the tools which are used. This is not Indian paper, finally. It's Chinese, but made with Italian scientists. Look, roughly 15% of the paper is explanation on how they recruited people, how they calculated the results, etc. And when we do managerial decisions, usually this is skipped. So most of the decisions I've seen in the business were statistically not significant, unfortunately. The good part of decisions in business, for example, again, let's take retail. Main driver of revenue in retail is increase of the number of stores, especially at most of the countries, the ones that are developing faster. So if the company is increasing amount of stores, even though they do wrong or unbalanced decisions about other things, the revenues are still growing. So they mask mistakes from one direction with stronger revenue with another one. With online retailers, it's slightly trickier. If they stop pouring money in the traffic, they're losing growth or revenue. So they have to control their financial and conversion rates as statistically significant all the time. So they use much more statistical procedures, which are often boiled down not to frequentist mathematics or Bayesian mathematics, but to cohort analysis, which we talked first part of the day. It's basically a substitution of trickier version with probabilities, which we're going right now. So, regarding inclusion and exclusion criteria, these guys wrote an interesting stuff. So basically, they excluded more than half of the participants, actually 2/3, 75% of participants, and then they did the randomization. So basically, it's one of the ideas was not to do that with stores. Randomized trials are always simpler to conduct. So the general procedure has to be very thorough. And regarding the statistical methods that we can find in the in the paper, it's basically the following. What you can see on the screen. Wait, I'll launch a slideshow. Yeah, so two-sample design is one of the variants of what we decided to do. Then two-sample t-test design is something that we cannot use because it's about paired samples t-test design. It's when we have the treatment group for the same it's the same person before treatment and after treatment. But there is a t-test design without pairs. So just one random group versus another random group. So in this case, they use the statistical tweak to work with humans. Alpha and power, we talked, it's basically statistical power and the probability of false positive result. Kolmogorov-Smirnov test is a test of normality. So we can enroll our data into t-tests, because t-tests do not work with data which are not normally distributed. And two-factor analysis of variance are the same stuff required again to enroll data into t-tests, because t-tests require data to have similar variance. Otherwise, we cannot use a statistical test. So basically, the authors have proven that the data is normally distributed, that the variance is similar, so they can use a statistical test, and statistical test proved that their treatment worked. That's a standard procedure of analytical decision making. And Cohen's D is basically a measure of the effect. It shows how far are the test group from treatment group. So we talked about this. Let's do a small exercise or thinking exercise on online testing. It is known that in online tests, delay is changing the results. So imagine you are a data scientist who have to compare the following. You have a page with something, advertisement, and you have a particular base rate conversion of clicking, for example. Base rate doesn't matter which one. So this is your control. And then you have the same page with machine learning model, which depending on who is coming on the page, it changes your object. So there is version 1, version 2, version 3. So for example, booking can change description of the hotel depending on who is coming on the page. Or sometimes they have a model which predicts travelers with children, and for them it pop-ups an alert, please do not forget to show to state how many children are coming with you. This is
Or they charge more for iPhone users than for Android users.
well, some ticket sellers. At least a couple of years ago, it was actually the case. Now I'm not sure, but it was before. So here we have no model. People come, see, and react. Here there is a background process which changes the content and tailoring it to the user. This takes time. So how would you design an experiment to be sure that your model works, but not... so how can you split the effects of time, model, and control? how would you design an experiment? Because if you add a piece of technology inside, it takes more time to load the page, so the bounce rate from the page can increase.
This is because we imagine that extra time affects a certain segment of our customer base, or does it matter that we care about how why do we think that extra time changes the?
I have, I think I put it aside, I have a graph that shows that delays in loading pages sometimes decrease the conversion rate.
For everybody.
For everybody.
Okay.
Well, not always, but sometimes it does, sometimes it is not. So we have to be sure that this time doesn't push us back in the quality.
Do we know this time?
Well, in particular model, yes. For example, 10 milliseconds.
As compared to control.
Yeah. So how we can test?
So you could add 10 milliseconds to the control.
First idea.
Yeah. Generally, this is the way big A/B testing companies are doing it. They are not adding actually a 10 milliseconds. They run 3 groups. Control. They add model here, but they do not use the outputs. So the model still runs, but there is outputs are not used. So there is it gives the prediction.
Oh, and then it just displays control anyway.
Yeah, it still gives the prediction, but it still shows the control. Those predictions do not go anywhere. And the third one, the model runs, displays the prediction, and prediction is used.
So control plus time. And then
Yeah. This is a standard practice to run A/B tests in the environments where a time is confounding variable. But it is 3 group A/B tests. It slightly makes statistics harder. So let's go through statistical methods, which we'll probably use tomorrow. Because I'm not sure if we'll have enough time today. So, layman's terms. So we'll not go into difficult statistics. Yeah. So first, we always have constraints and statistical too. When we are on the manager's seat, the more we know potential constraints, the crisper the more precise decision we can make based on data. For example, if the constraints about distributions in the data that we are comparing. So we have to be sure that we're using right tools. And basically for different kind of variables, we have to use different tools. Continuous is one set of methods. For discrete variables, there is another set of methods. They can be similar. The difference in Python is 3 words. But very rarely you can use same method for both variables. You cannot use same test everywhere. Here is what we talked at the beginning, a few hours ago, about checking linearity and monotonicity. It's the Pearson correlation and Chapman correlation. That's linearity, monotonicity, and dependence on variables. It's chi-square test of independence. So, depending on what we do, we have to deploy another test. In this case, it's not a big deal. This is 3 standard tests which are used everywhere. For time series, there is another problem. When we're saying a time series, we assume that the process is autocorrelated. but we do not know if it is autocorrelated. So before using mathematics for time series, we have to be sure that they're autocorrelated, and there are statistical tests. There are a few of them, and I think they will be out of scope of these lectures, but we can go through it. This is three basic tests. And we have to check if distributions have same or different parameters, otherwise we cannot compare them. Or otherwise, comparison of them leads to very significantly higher probability of error. So we'll look through the two-sample t-test design. This is actually the one that is used in the paper, medical paper. So, yeah. This is same but with methods, which we will skip because we will use some of them in practice. But there is another interesting thing. In the paper, the authors, used this test, Kolmogorov-Smirnov test. And when you start to dig deeper in data and methods, you always find unexpected things which you didn't know before. So in the paper that we briefly checked, there was a test for normality, this one. This is just a list from Wikipedia. But when we go to guidances for statistical methods, this test is absent. And actually, there is a reason. Because it works well when mean and variance of the normal are assumed to know under the null hypothesis. So we have to understand a null hypothesis in the case of the experiment is not only the control group, but everyone who snore. So very often Kolmogorov-Smirnov test is not recommended to use, and they substitute it for improved version, which is more heavy in computation, which doesn't matter right now for some advanced method. And if we check the guidelines would look exactly like this. The first one is Shapiro-Wilk, and then depending on what you do, you can pick any methods. And test for normality is one of the most troublesome parts of the statistics, or at least applied statistics. And even improved version of the test that was used in the paper is in the last place. And there is no classical test. Kolmogorov-Smirnov. What it means for the paper?
I don't know much.
Well, yeah. With Bayesian statistics, it means that they were using. They used to do science. They took a statistical package. Kolmogorov-Smirnov normality test is everywhere. They used the first method that everyone used for 10 years without really understanding what is underneath. Okay, so it explains something about their knowledge of statistics, but what it means for the outcomes. I'll tell you the paper. I'll tell you the contents of the paper.
What's the size of their group? They had 25 people in their group, so it's not necessarily very useful.
If we're talking about more advanced statistics, it's better than 10 training centers that we're trying to compare. But in biomedical studies, 25 starts to be fine. Because t-test statistics usually works even with slightly smaller samples. Basically, what they're stating, that they took a big group of people, they selected people who can be in the trials, they picked them, divided into groups, control and trial, trial. So they measure their snoring. Actually, it's not about snoring. It's about how they stop breathing during the sleeping. Then a test group did exercises. And then they measured again. And they have found out that now they were equal, and now those guys snore less, so it means that they have gotten better after the exercises. So this is basically what happened in the paper. What means their choice of unfortunate Kolmogorov-Smirnov matrix, which has less power than its peers?
It means that the conclusion could be wrong.
Right. So basically, how it works? They measured something. It's paired tests. So basically, same person here, measurement here is corresponding to measurement here. Measurement at the beginning of the experiment is corresponding for the measurement at the end of the experiment. Non-paired test would be separate. We would compare distribution to distribution, and now we can do distribution with pairings. So this comparison shows how much better they're getting. And this method of deriving that this is better relies on the assumption that the data is normally distributed and the variance is same. So basically, we are increasing chances of fetching into the method that works only with a particular kind of data that are not as good. So it actually decreases statistical power of the whole experiment.
Mm-hmm. But if it is only 25, maybe we can see if there was only improvement or also somebody started to snore
more. Yes, it's two-sided test. If they conducted two-sided tests, you actually know if you went this way or you went this way, and you see it directly with.
And we have this kind of test for small samples.
Yep. But basically, you repeat the same as in paper, but you preferably do not do this test, but you do or this one less than 100. Highly recommended, especially when you use a conjunction with a normal probability plot. You do normal probability plot, you check by eyes, you do this test. If you get all these test metrics, we will see soon in Python, they give you a test statistic, a number of the test, and probability p-value of null hypothesis, or actually alternative hypothesis. So basically they say how much they believe that the distribution is normal. They give exactly the same responses. All of them, and most of those tests have the same outcomes. But again, abstractions leak. And this is how they leak. That this works. This size, this one. So this size, this one works only if everything else is unavailable. So without actual implementation, the more we go into detail, the more troubles we will have. So we've seen this slide.
So, and in this particular experiment, there was actually nothing stopping them from using a better method.
No, nothing. They could just switch the formula. Instead of import Kolmogorov-Smirnov, they could write import something else.
I wonder if it would make a difference in this one. Interesting to know.
Frankly, do not much, because the effect was pretty significant. Especially they were doing it on patients who had a stroke. Probably they have not good coordination. There are a lot of things. But if the effect would be small, like in some business decisions, especially if you're a data-driven organization, your decisions are getting less and less and less returns. So your methods of doing decisions have to be better, better, and better. So in this case, in the case of paper, I believe that it doesn't change much, especially because there are other papers that claim the same for other types of patients, non-stroke ones, slightly different exercises, but it doesn't really matter. There are other things. But there is a trouble. When you check research in biomedical studies, most of the research is not reproducible, kind of the outcomes. Why? Because of either there was a bias in experiment design, or there is a problem with statistics. For example, they have gotten a false positive result, published it as false positive, and it is possible, because here we fixed the false positive rate by 10% probably. So there is one chance out of 10, there is no effect, it just happens. Well, in this case probably it's 5%, not 10%. But still, one of 20 treatments like this do not work, and this is still science. Let's see one thing, or why not? I think we have a break, where now is 5:35. We're supposed to have 10-minute break. Какое у нас расписание? Потому что у меня здесь другой календарь. I'll check.
This is a lot of exercise.
17:30.
It's a good time to do it.
Yes, можно
The actual exercise is.
Okay, so we can do a break for 10 minutes, and then we will start with basic statistics. During the evening, I'll recalculate your case. Are you checking the paper with exercises?
Yeah, 200 sticking out my tongue. 3 times a day. 200 times you have to gargle without water. I don't even know what that is.
It's Chinese. Chinese. This is a particular group, people who had a stroke before, so probably they have problems with coordination.
Yeah.
And they were measuring, not snoring, they were measuring apnea during the sleep. And if you will check the...
Only one guy quit.
Yeah.
One guy said, I'm not doing this tongue thing. That would be you. Have to snore.
Then there is an interesting stuff here.
But
They enrolled people in the research which stopped breathing between 15 and 30 times an hour during sleeping.
yeah, that's a lot.
It's not just snoring, it's actually stop breathing.
It's not breathing. No, a lot of this sort of this power thing, it points to like one of your very first statements, which is like figure out the first thing and do it. Especially for like a small organization, like you're actually not able to do the experiments if you're only. I mean, if a 100-location business barely has enough. People
Well, 10% or 10 versus 10%.
Yeah, but I mean, it's, 100 location change is pretty big business.
That's exactly it.
If you're a 7-location business,
But you need a continuous monitoring of the metric. So basically you are doing experiment
non-stop.
live,
Да, мой, конечно, выжил.
and you have to measure where it goes.
Where it goes. Yes.
Not during the experiment, because you have a false positive rate. full stack integration.
Точно перенесли. Перенесли
Big
маркетинг на
companies, they do not do the investing and then sign
маркетинг, я думаю, что какой-то курс не перепутал. На июнь теперь
post-launch monitoring,
который мне точно изначально.
and some of them are using
А все остальные курсы кончаются вот здесь в мае.
effect after putting it into production. Was positive or something changed around the world, and it's not uncommon. It's actually a standard practice.
To not monitor.
Сказать, что
Yeah, to monitor.
маркетинг может быть.
I mean, it's standard good practice.
Oh, yeah, I know what you mean, but it's standard actual real work practice.
No, it's not. If we're talking not about booking Skyscanner,
Я говорю, что на маркетинге.
big and powerful e-commerces who spent 3 years developing their A/B testing platform.
It's also simple for them. It's easy to do this. Like
It's
how do you do A/B testing in car sales? You know.
Июнь такие.
you do statistics. You do sales statistics as in biomedical studies.
Правильно? Я хочу.
So you basically have either online trials,
Или надо или
but building you either have to buy something like Optimizely, which costs a fortune, or use very limited tools, or build your own. So all the companies I know build their own, which takes them like 3-year project or as developers. So A/B tests are hard. For example, there is Preply in Kiev, a company called Preply. Preply. Mhm. They are doing. It's a platform for tutors. Yeah. They are roughly doing 100 tests a month. But they have their own platform, which they wrote by themselves, consulting with bookings. But when we're talking about the real businesses, there is not much monitoring. Because technically it starts to be...
What's I'm saying? It's easy to these guys are
it looks easy, but then when you have a variety of tests, it starts to tricky to store data, to analyze data, to roll out variants.
No, but I mean, it's like the, if you think of like, to do this test, not to do this, just do this test, just actually make this happen, like hiring other people, training other people.
Yeah, you just
go, start.
yeah, in booking it looks like a team of roughly 6 people who are responsible for testing a hypothesis. This is a project, there is a copywriter, designer, couple of developers, data scientists, that's it. And they do X tests a month.
And there's no manpower for implementation, right? Like once it's running, it runs by itself.
If you write properly, but there is a lot of propensity to make mistakes when you're building the general architecture. But if it's right, then everything goes fine.
And so you could, that's why you can do 100. Because you write it, let it run, you write it.
Companies like Booking doing thousands any given moment of time. Like thousands, but not thousands, but roughly. But building the platform that supports it is non-trivial. But when it is there, it gets way easier.
We do A/B testing just for email communication, like we're using mail trips, sorts of tools. The difficult part is the copywriting and the figuring things out, not the implementing.
Let me send another piece of the code with statistical functions.
Да, буквально, мы уже давали сегодня. Ну, когда представили возможность,
Про всем курсом.
Ну, мы уже предлагали маркетинг.
Это, конечно, не есть. Так, это я посмотрел, это что? Ския. Они были не обязаны. Почему такие рады? Из вас пожалели клиенты. Это у нас есть. Чищу. Хорошо. Фрилансер, фабрика, присоединение, описание. Меня представляете. Ты ведешь на грамм?
Я не знаю.
Кстати, у вас выбор избирательных курсов.
Да.
Analytics for Finance и одновременно Analysis for
У
Finance.
нас у нас есть.
Segmentation Customer. Вот этот ты
Да, вот
хочешь.
это я хочу.
You mentioned
Ты
that.
хотел уже провести листовик.
Конечно, я еще.
I wonder,
Что это?
let's see. Who hired him?
Я не выбрал, но я попросился на дополнительный туда.
$14 an hour.
Я не помню, какая скидка есть.
Ну, что-то, мне кажется, 1718.
Не знаю, что это 24.
Ну,
А
займемся
то есть
скидкой.
скидка.
Would be the same beer because before.
Спасибо. То есть, что я должен сделать? Я должен попросить вычеркнуть что-то отсюда и включить себе
Да.
advanced analytics, да? Можно. Или купить его. По поводу ритейла я должен почитать, что было в ритейле.
I think it's what it is, that there's lots of them and they speak English. So that's what I showed with these things. There's probably lots of Chinese people that don't speak English.
От какой получил письмо? Актуально напрямую или все-таки в песне?
To have good education, you don't need lots of expensive infrastructure. You just have one piece of paper and a guy at the front can teach you.
Здесь.
But I think that there's more, there's not more people in China.
Слушай, это могло быть в декабре?
Ну, реально. Да, могу. Да, могу.
Thursday. Then on Friday.
Не забыл позвонить, конечно.
Are we,
Делайте курсы.
are we gonna do any case studies on this weekend?
The big ones probably no, but we will work with simulations, etc.
Yeah, but no, not existing ones, not,
They actually existing ones. They all existing ones. For example, the one that we will continue tomorrow with
based on this.
evaluating the consultants. It's slightly different source, but exact situation in one of the
The
businesses.
upselling one?
У меня здесь нет.
Exact situation.
А, вот центр. Customers.
Да, да.
Это что?
Customer Center, это
О, маркетинг позади.
маркетинг не первый, маркетинг не ритейл.
I need to look at my calendar.
Ладно,
Everyone needs to be somewhere in May.
можете что-нибудь добавить?
strategic patterns over achieving patterns. That's good.
А, Excel. Делали. Так. Так у нас будет два вектора на Customer Centric Analytics. Вот этот мальчик. Либо нет.
Кстати, может рассказывать.
Джентльмен.
Oh, okay, I'll have to.
Вы брата не знаете?
А?
Брата не знаете?
Что?
Ну, кто будет рассказывать? Вы брата не знаете?
А, нет, я имею в виду, что он может похожие вещи рассказывать на пятигодный анализ в этот момент.
Горячий.
So we can start. So I think we can start. I'll share the screen. You need to download a file from the same folder. Yeah, and open it through IPython notebook. Tell me when you are ready. So, we will go through almost all statistical methods that we mentioned during last 1.5 hours of discussion on dummy data. And you'll see what is the difference between one statistical method and another one in terms of implementation. So for the normality test, we are. I thought I shared the screen.
Stats. Is it correct?
Yeah. So for the normal distribution, if you need, I can make the bigger font on the screen. Because I can see almost nothing. I have a script here. Anyway, here's a histogram of something. Does it look like normally distributed data?
In my case, yes, because I have another.
I use it.
Well, in this case, it's also normally distributed data.
It's random, yeah. Randomly generated.
Yeah, it's randomly generated, and even this is normally distributed data.
Okay.
Scale is 5, and location is 10, so the center of the properties in generate normally distributed data. We're generating is with NumPy, we're getting NumPy array, which is normally distributed, and this is...
Definitionally, it's normal.
Yeah, its definition is normal, random normal. So the scale is 5, so basically it goes left and right from 10 by 5. The trick is when we get to smaller distributions, true normal distribution, which is very wide, would look like this. Surprise, surprise, this is normal distribution. And that is what is happening if we have wide data set, kind of wide distribution, and small amount of sample sizes. If we will make scale way smaller, it would still will be a disaster. But if we will zoom out, it will start to look better. And I'm not sure if it will work out this way. And the only thing which helps is actually
Sample size.
increase the sample size. So scale 1, size 20. It still doesn't look like a normal distribution, but the generator actually generates normal distribution, and that's a problem of small samples. So when we're aiming at comparing a sample with sample size 10, it doesn't look good, frankly. If we are,
So what does scale mean in this
scale means
distribution? What statistics is?
so location is 10,
Yeah.
and scale means 5 and 5 here. So this is the whole distribution. This is not statistical distribution. This is 3 sigma or something. That's 3 sigma left or sigma right. So basically where the distribution ends. And in this case, with a small sample size, it didn't even fill all the brackets.
And there's somewhere outside of the scale.
No.
Well, it shows 1 basically. We can check the data.
5 it is number of
Yeah, it goes slightly outside of the scale, because scale, I think it's 3 sigma left, 3 sigma right. So basically most of the distribution. But anyway, your normal distribution when you have small amount of samples will look very, very not normal. And that's the fact that you would hunt you with any small sample. So how can you check that visually check that distribution is normal? The simplest method is to plot a histogram, which would not work well, or QQ plot. A QQ plot is basically a plot of the ordered quantiles, actually percentiles, of the values versus theoretical shape, which have the same scale.
Pylab.
From Pylab, yeah. I've
Dialog is only
I'll have not defined.
I'll wait.
Need to get more of it.
Let me fix it. Let's try whiteboard. Ta-da! Fixed everything. So here's your whiteboard. What would happen if we will go through a really weird distribution like this? This looks almost like normal. You see, R square is basically a degree of fitting with how red line fits the line is represented by blue dots.
It's easier to see that it's normal than with the histogram, that's for sure.
Yeah, here we see something really weird. Between 8 and 10 everything looks fine, but everything else is not fine. So, and here we see an R square of 0.92, which is almost fine. I mean, it depends on the case. Most statisticians say that R square here is almost meaningless. But I used it a lot in applied statistics. It is dependent by a case a lot. Because, for example, when we did simulations of the chemical reactions, we were aiming at 99. And 98 or 97 indicated that something is wrong at the beginning of the reaction, and our theoretical shape do not show the kind of theory do not fit to practice. But because we have a lot of big part of the curve was standard, it was very easy to fit with the formulas that we used to fit, and the small part could just have different slope. In this case, we have just 10 points. This is fine. 92 randomly generated points. Then, there are other normality tests, which now we came to Shapiro-Wilk normality test. Is the one that was the most recommended by Statistics Handbook of Environment Protection Agency. And as you see, we import Shapiro. We take the top tuple, so two values, statistics and p-value, and show data to our statistical test. That's it. That's the whole normality test.
Yeah, but which data you showed? This
Same data, yeah. And I showed the data which looks like this, really weird ones. And what our statistical test shows. First, all tests want an observation in each sample independent and statistically identically distributed. This is everywhere. So every time we're doing a particular kind of sampling, which is not independent, or we can sample the dependent variables, our statistical tests start to fail. They still think that the data is independent, and we have starting to get troubles. And then in all tests we have same hypothesis. Base hypothesis is a Gaussian distribution, so normally distributed data, because Gaussian and normal is essentially the same. And alternative hypothesis is not Gaussian distribution. So we run tests. If p-value is bigger than 0.05, it means that H1 is rejected. So in this case, even with very noisy data, our p-value is 31%. It means that the chance that that alternative hypothesis is true is tiny, or relatively tiny. So it looks like normally distributed Then another test. Basically, we import same comment. We change basically what we import. We import normal test. That's not the same that we changed. It's also normally distributed.
It's there.
Yeah.
Oh, because n is too small.
Hmm?
N is too small, it's error.
Yeah. Let's
It
make
wants n of 20.
20.
Not normal.
Yeah, I see. It says that Shapiro test says that it is probably Gaussian, but 0.059. So it's on the verge of being not normal. But in reality, we generated a normal distribution. So these tests fail, and they fail a lot, especially in the smaller samples. So one of the statisticians' recommendations, especially for managers, is to run all three. If one fails, then there is not enough hard evidence for the normality. But otherwise, you have to really understand what is happening under the hood. And the last one gives multiple results with a different critical values. And because we have a small amount of data, our system thinks that it's not Gaussian on particular confidence levels. You see?
But it is the 1%.
Yes, that isn't 2.5, no?
Yeah. But at 15 level of confidence, it thinks it's not normally distributed.
1% confidence.
Yeah.
Okay.
So basically here we bring significance level and critical values. Critical values is your confidence interval. It's the one that we talked at the first part of the day and mentioned. If we'll have more sane distribution, like 200, this test will pass everywhere. That's it. So the less values you have in your experiment, the more potential troubles you'll get. So then correlation tests, the one that we talked, they are slightly, here we have to be careful with assumptions. Everywhere observation in each sample has to be independent and identically distributed, because correlations work when each sample is normally distributed and have the same variance. Again, if something is wrong with our sampling or experiment protocol and our variance changes, this stops to be efficient.
And what are the examples of some like common mistakes in sampling that would cause variance?
Non-random sampling, biased sampling, whatever. So, for example, if we sampled data by similarity of the stores and they still apply the same statistical tests,
Okay.
I'm pretty sure that the statistical test will overestimate the effect. So, here everything is very simple. These two distributions are dependent because the p-value is 0.28. 0.028. So Spearman is, we talked about Spearman's correlation, is the measurement of monotonicity. So it actually means that observation in each sample can be ranked. That's exactly what it implies. So if we do not care about linear relationship, but we care about the rank. Same stuff. Everything is ranked well. And chi-square test, the one that we mentioned also, the one that most of companies do not use. It's the test of categorical values. That's it?
Probably dependent or probably independent.
Well, probably dependent, it's just a print. But basically we have gotten p-value of 0.97. That's it. Then next, we'll click through very fast. Parametric statistical hypothesis testing. Parametric statistical hypothesis tests are used when your distribution is normal. You cannot use them on weird and random. Oh, I have forgotten one thing. One neat thing. I wrote it in the text. In quantile to quantile plot, you can change distribution. So you can visually check not only normal distribution, but any other type of distribution. So by just changing what is highlighted, the type of the distribution. Let's see if there are in the documents. I'll zoom. Stats distributions. Look, we are going to the documentation. This is SciPy documentation, and it says that it takes objects that looks like stats distributions. And stats distributions are this is all the distributions that we can use. Well, this is not distributions. Let's see. Yeah. So here's continuous distributions. We have pretty good choice of them. In real life, we will have very small amount of distributions, but basically the function is built that it accepts any model distribution. Sometimes you have to fit the scale, because it's not always fitting the scale, so you have to show to modeling the theoretical distribution where is the expected maximum. That's it. And the trick is that in Python you can do it not only in SciPy, but in a few other packages that are abundant. Yeah. Anyway, let's go back to where we are. Parametric statistical hypothesis testing. And here we have a few things. First of all is, again, independent samples and identically distributed, normally distributed, and to have the same variance. We have two data sets, and we ask the t-test to say if they are the same or not. That's it. That's the whole statistical test. So basically, most of the statistical calculations in mind are counterintuitive, but when you have the right data in Python, they are very simple. Here, the next one is paired students t-test, is the one that authors used in the paper, which means that each entity is measured twice before and after the treatment. This is possible to use in business. For example, when you, say that the revenue on, let's do a simplified version. Revenue on Tuesday is the same. You do the Tuesday without the consultant, and then next week you do a Tuesday with the consultant. This would be a paired test. Store to store. Store before the consultant, store with the consultant. The trouble is that confounding. troubles are in compounding values. In this type of setting, we do not control them. We hope that in one Tuesday, nothing else changed.
Yes, but you label the side change or something.
Yeah, or next Tuesday is a holiday, for example. So then we have to do an extra mile with what is different. That's why any biomedical research puts very strict rules, what is happening before, after, when, etc. So we are limiting things that might influence the outcome. Yeah, same one-liner. Then ANOVA. One way ANOVA works with three groups. That say means of the samples are equal, or one or more means of the samples are unequal. And then you have to do pairwise, the standard protocol, then you do pairwise comparisons. That's the whole ANOVA. Import F1 way, data, data, data. That's the whole hassle. Then final part is non-parametric statistical hypothesis test. Non-parametric one you can use when samples are identically distributed, but distribution is not normal. For example, you have something like this. Non-parametrical statistical test would say, is it the same distribution or not? Or if you have something like rainbow distribution, whatever you have, but you cannot use the ANOVA, for example, only for normal values. Here, same hassle. Import name of the test. The difference here is that in some cases, as everywhere, samples can be ranked. In other cases, well, here they are both have, yeah, here they both have to be ranked. So that's it.
And so what's the example in real life of ranked samples?
Ranked samples means that, well, ranked samples is when you do not care about the vertical scale, or you care less about the vertical scale. Let me think. Something from which is not normally distributed. What can be not normally distributed was what we worked a lot. Survival models. Survival models is sometimes, this is one of the models that are used in predictive maintenance. They basically, they have very different distribution. They show how population in nature dies, or how physical parts of the machinery start to fail when you have a high population of them. So first everything is okay, and then there is a part when they start to fail. So this is a not normally distributed data, and you cannot use, you have to use another statistics. And here you need, it's ranked, because every next point has to be, your failures are ranked. You have one and one less part of the machinery which still works. So what else?
That's
Yeah, I would say that's more than enough. Then there are 2 or 3 more tests for stationarity of a time series, which actually looks exactly the same. I'll add them to this document for those who want to click through. And now let's do the following. We still have a few minutes. Let's try to take our use case of the testing, which of the fitness center tests, and write the protocol of how we can check if the sales become better. What do we do? Theoretically, if we're talking about revenue, right? Revenue.
Yeah.
Revenue in randomly selected samples supposed to be normally distributed. So we have control group, control and treatment. We do not fix ourselves on number of stores right now, because this can be a limitation for statistical tests, but this is not our problem right now. And more, it's out of scope of everything except the statistical course, which will be not useful for any of us. Well, generally never. If it will be useful, you will know that you have to open the book and yeah. If you see that the Python says a sample too small or the distribution is weird, then you open a statistical book and start to read. That's it. Otherwise, we will stuck here for the next months learning statistics. So we have control and treatment. We have to be sure that sampling is random and identically distributed. For this, we have to do, well, and that it is normally distributed. We have to take data on revenues for these stores. After, for example, before or control group and treatment group. So we have data set which looks like this. Store ID revenue, store revenue, kind of store 2, store 3, revenue, store 4, revenue, etc. Here is the same. First we have to do normality test. So our revenues are normally distributed. Hopefully they are. Which test would we use?
When I just bought it.
Well, first you plot, and then yeah, probably from those here we have to use Shapiro would work. Then I haven't included the tests on the variance. We actually have to measure variance. If we're not sure about the sampling distribution, Shapiro, it's normality. Then we have to measure variance.
And how close is, so same variance, like how close is same?
Because the statistical test same as almost same protocol, it says it's the part of the same distribution node. It can be slightly kind of, in some cases even statisticians are allowed to accept more kind of not so strict rules. If we see other arguments why. For example, visually we plot one and another one over the same mean in the same scale, and we see visually that they actually do not seem so different. This is enough for managerial decision making, but if we plot that they are very different, something starts to be wrong. So we have to measure variance. So if we know that the tests, the normal and the variance are similar, then a student's t-test, we have independent, identically distributed sample, normally distributed, same variance. So we run t-test. 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 What t-test would give us as the response?
P-value.
P-value of what? Well, it is zero.
Hypothesis, no?
There is the dimensional freedom, different dimensional freedom.
Actually, t-test, the one that is high-level t-test, even do not give you dimensions of freedom. It says it's a member of the same distribution or different ones, and the statistical significance. So if you will do a t-test, it can give two answers. Either they look same or different. If they're statistically significant different, then we just take the center of the distribution and we can measure the effect.
Whether it's up or down.
Yeah, both ways. That's the simple way. There is another potential protocol. But it would have much more confounding values, is to put consultants and to measure the sales before and after. So it has to be a very short span and see if something has changed. But we can do a regression analysis.
So when I have my question about like what variance, so how close can variance be? And I mean like in the real world sense of actual business data you might come across, what is the effect? So let's say the variance is they're a little bit apart from each other, maybe not ideal. What does that effect then have on the t-test results? The variance of this.
T-test starts to be less. It starts to give you more false positives.
False positives.
Very often, if inputs are rubbish, then the tests are getting overly optimistic.
So optimism is the direction of failure.
Yeah.
Okay.
This is at least in all the manuals I've seen. Most of the cases it's stated that it goes to optimism, and optimism in this case is what we have to afraid, because we usually expect improvement.
So waste of efforts, waste of resources.
Then that's actually it. And now I'll switch to another screen. Look what we had in our paper, what methods were used in the paper about snoring. A design that we made, alpha and power for calculations, test for normality, test of variance, t-test. So basically check if people stop snoring is the same if consultant starts to sell more. There isn't much difference. This helps to understand how big is the effect in statistical terms.
But in this case, as a control, we used
People without
paired sample test.
well, here's paired because it's for the same person.
Why not to use paired here also?
Because we might need to have longer time for the revenue. So confounding variables can spoil the result.
Okay, it means that if the business is seasonality driven, at least to be.
You have to do
But if not,
if it's stationary, then it's fine. you have to be sure that anything else would not intervene with your experiment. And pilot 1 would work as well. You had kind of no treatment part, it was like this treatment part. Even with treatment, it doesn't matter if it's after treatment or during treatment. If it's changed, you'll see. But because this is time, another day of week, another month of the year, another year, etc., we're starting to have troubles. We can weight those troubles by using kind of time series analysis. For example, we have a time series fitted, then we have gotten a consultant, and kind of something good happened to our time series. But this requires way more troubles and computations than just split in two and do t-test. So in this case, it's either time series plus change or regression analysis. So basically we check all the confounding factors, or all the factors that can influence, like day of week, sales, is it the holidays, this isn't changed. Yeah, and then we add another variable which we added, and then fit the regression and see, oh yeah, kind of the weight of the new factor is 0, so it didn't. But then we're working in the situation of the mixture of the factors. It works. It is used somewhere where you have no choice, like sociology, where you cannot weight or remove other factors because it's about society or other things. In business, you can do random sampling, and that's why regression analysis is not widely used in companies with A/B test-driven cultures. I mean, regression testing it's called something else. It's a type of the test of software. It's nothing to do with statistics. Yep. So that's the trick. And now, what we haven't taken into account: variance can be small, or variance can be big. And this variance will influence the test. If the variance is big, we have to see either very high effect or we have to have very big sample. If the variance is small, we will see a small effect as well.
But this control group, it is in our hand. We can take the branches more or with the same level of the revenues plus minus with the same number of customers.
Well, in my experience, it's biased. I mean, the analyst comes and explains, I do the same, have the same sales, etc. Then we're starting to put a statistical hypothesis. Kind of, for example, they sell different kind of goods with the same ratio. For example, on each deodorant they sell, one shampoo. Mm-hmm. Probably, if the businesses are the same, it has to be the same ratio. We check it, and it is not. So something is different inside.
In this case, better to increase the sample to 50. Then
if we can.
Yeah. Then to pick the branches.
We do not know the variance. If variance will be by chance small,
yes,
it's fine.
If big, of course, if the
variance is big, maybe even 50 would not be enough, and we would have to wait many months for the data to come.
Okay.
So basically, this is what I am worried here is number of data points in sample and how big is the variance. So if I hope I will have time, or we will do it tomorrow together, I want to show how variance influences the results of the test. Because it will. Yeah, that's it. So, data-driven decision making doesn't really differ from ordinary science. You do not need to know, or even biased but more or less proper calculation is better than guessing. I think that's it.
Thank you.
Well, that's it for the lecture part. Do you have any feedback or things that you would like to share?
Maybe tomorrow.
But what we will have tomorrow? Because there was no syllabus yet, I think.
Yeah, I'm changing syllabus depending on inspiration. I'm intending to go through a bit more simulation of this, A/B testing, and actual A/B testing, not t-tests, but how A/B tests work, a culture of A/B tests, so it goes from the code to the companies which can support decision making based on analytics. Then probably we will have time for the question that I asked today to talk about engineering practices. 1.5 hours. And I hope this will be tomorrow. And on Sunday, I think we will check machine learning part of decision based on data. So we will fit a couple of models and see how thresholds in those models, etc., can influence business values.
And we'll look at the actual case here.
Well, this is tomorrow, the actual case.
Yeah, tomorrow.
Can you tell us about AI Lab?
Yeah. So we have a small initiative in the Kyiv School of Economics. We're trying to gather some use cases from, well, not use cases, but some data sets and pains from industry to supply it to the students of Kyiv School of Economics who have to do capstone projects with a particular mentorship as a material for capstone projects. But they will be pretty difficult, I would say, because this is an actual, not a simplified use case, what would you do with stamp stores, but an actual industry data set, if we will get some hands-on of them. But hopefully we will.
What's this thing called?
AI Lab. But this is basically a volunteering and trying to start cooperations with city administrations, data providers, etc., and to solve some of the real life issues during the capstone project. We do not know how it goes, how it will be in the data yet, but this is what the Kyiv School of Economics is working on.
What's the data set?
Well, it can be very specialized data set that it's difficult to use somewhere else, but still the actual pain of some company or a city. I'm not removing everything on board. I still need it.
I'm afraid that we should put kind of sign. Для уборщицы надо написать на бумажке и прилепить чем-нибудь, я предлагаю, потому что...
DNE.
Такое было?
Ну, это...
Do not erase.
Ну,
But that would work too.
and we can make photos.
We could, but then you have to read it as fast as possible. And now I have a word called.
Может, закроем снаружи налево? Так нормально?
Потому что нам же нужно будет пройтись по всему, что нас выдавало. Спасибо, это было круто.